you can go master calendar website somewhere that you can look at and see like the calendar for the next like 4 or 5 years. But it's also, yeah, it's set up and also it has to like, most of the calendars are set up to coincide with the other UC, so we don't get like far off from each other. So most of the UCs have pretty much the same holidays and start dates and stuff like that. Merced and Berkeley being exceptions as they're both on semester. But yeah. Yeah. Hey, Maggie.
I can't stay because I
That's okay. You don't have to stay.
like 5 hours of sleep even though I slept early.
Okay. Yeah, I mean, you're welcome to watch the video later. It's totally fine. Or not watch the video later. Whatever you want to do. Totally okay. Have a lovely Thanksgiving.
Thank you. Have a good day. What? I want to sleep.
Cracking me up. Here's the attendance form for all you folks on Zoom. Gotta do that. Do you all have other classes today on campus? Yeah. Oh, yeah.
My 11 a.m. That's why I always leave it.
Oh, sure. Yeah. Well, yeah. Let's see, I should get them. I got new pens finally. It finally came. Very happy about it. It's not like easier. I'd have to pay for them, so it was okay. They weren't that expensive. Let's see here. Yeah, I feel like I'm missing something here. I guess not. This feels weird. Okay. You. Got you. Actually, I'm gonna start on page 2, just because page 2 makes more sense to start on for this particular stuff we're doing. Come on in. All right, let's get started here. Just a couple of reminders, just so you all are aware, if you're taking math 16A or 17A or math, I don't know, math 12, maybe you need, I don't think the placement test for math 12, I'm not sure. Anyway, if you need to take the math placement test for whatever class you're taking next quarter, you can take the math placement test once during essentially the week of finals and once during essentially the first week of winter quarter. So I believe that it's actually like literally essentially finals week is when you can take it, and then again during the week of the first week of class. For more from and actually, you know what I should do, what I will do is I will post a link on Canvas so you all can like have the information more easily available to you. But hopefully, probably I'll take the math placement test at least once already, maybe. So it shouldn't be super new to you, but if you have any questions, you're welcome to ask. But trying to remind you of all that, you'll have 2 shots to take it. So there you go. All right, let us look at class W, some more trig identities. And I want to start on page 2, just so we can start with actually a little bit more important. Noting specifically here, if you have sine of an angle plus another angle, and this is also true for cosine, that it's not equal to sine of an angle plus sine of the second angle. So sine of A plus B is not equal to sine of A plus sine of B. And similarly, oh, that's not the pen I want. And also, cosine of A plus B is not equal to cosine of A plus cosine of B. In general, right? Occasionally you can find some angles that might make this true. Just like occasionally, right? In general, I will point out just as a kind of similar example, it is also true that the square root of x squared plus y squared does not generally equal x plus y. But occasionally you can find some examples for x and y that make it work. Like you can certainly say the square root of 4 squared plus 0 squared is equal to 4 plus 0. So sometimes you can find examples that work, but in general, it's not always true. Same deal here. In general, sine of a plus b is not equal to sine of a plus sine of b. Let's look at an example because I really want you to believe it so that then when we talk about the other formula, you believe it more. So let's look at, that's fine. So sine of, let's do 30 degrees plus 60 degrees. And I'll point out that sine of 30 degrees plus 60 degrees is just equal to sine of 90 degrees. If I bust out my unit circle here, 90 degrees is at the top of the unit circle, where the point is 0, 1. So the sine of 90 degrees, 0 or 1? 0 or 1. So I'll remind everybody, when we're on the unit circle, the x coordinate is the cosine value and the y coordinate is the sine value. Or as I like to think of it, it's alphabetical. X before y, cosine before sine. So sine of 90 degrees is definitely equal to 1. But if we look at sine of 30 degrees plus sine of 60 degrees, it's not going to equal 1. Sine of 30 degrees is, I'll be great. I like the little triangle still. Here's my 30, 60, 90 triangle. And the sides are 2 and 1 and square root of 3. Sine of 30 degrees is 1/2. And cosine of 30 degrees, sorry, sine of 60 degrees is √3/2. And 1/2 plus √3/2 is definitely not equal to 1. It's equal to 1 plus √3/2, which is approximately, I don't know, 2.7/2, which is approximately 1.35, which is not 1. So I really want to just stress here, sine of 90 degrees is equal to 1, and sine of 30 degrees plus sine of 60 degrees is not equal to 1. They're not the same. Okay. So what is sine of 30 degrees plus 60 degrees equal to? Well, it is equal to 1. And there is a formula that you can actually use for the sum of angles. It's called the angle sum formula. It's written down here below. And so let's actually show it here. Sine of a plus b, sine of 30 degrees plus 60 degrees. I should point out, you would never actually use this formula to calculate this. If someone asked you what sine of 30 degrees plus 60 degrees, you would add them together and get sine of 90 degrees and then use the unit circle or whatever triangle is appropriate. We're just trying to show it's true. So sine of a plus b is equal to sine of a times cosine of b plus cosine of a times sine of b. So sine of 30 plus 60 is going to be sine of 30 degrees times cosine of 60 degrees plus cosine of 30 degrees times sine of 60 degrees. And let's see if that's actually equal to 1 like it should be. So looking at my 30, 60, 90 triangle again, sine of 30 degrees is opposite of hypotenuse, which is 1/2. Cosine of 60 degrees is adjacent of hypotenuse, which is also 1/2. Cosine of 30 degrees is adjacent of hypotenuse, which is √3/2. And sine of 60 degrees is opposite of hypotenuse, which is also √3/2. And adding these together, well, 1/2 times 1/2 is 1 times 1 over 2 times 2. And √3/2 times √3/2 is √3 times √3, which is 3 over 2 times 2. And 1/4 plus 3/4 is 4/4, which is 1. Check. So it is true that sine of a plus b is equal to sine of a times cosine of b plus cosine of a times sine of b. And it's also true in a similar way that cosine of a plus b is equal to cosine of a times cosine of b minus sine of a times sine of b. There's actually 2 other formulas here that I like to kind of like to write them lazily, but I'm actually going to not. So it's also true that there's angle difference formulas. So sine of a minus b is equal to sine of a times cosine of b minus cosine of a times sine of b. And cosine of a minus b is equal to cosine of a times cosine of b plus sine of a times sine of b. Or as I like to think of it, for the angle sum formulas, these are angle sum formulas, or identities if you prefer. the sine formula, I wish whoever named the trig functions, I wish they would have picked a different name than sine, because I want to use the word SIGN to say things. So what I would say is for the sine function, the sine of a plus b or a minus b, that sign there stays the same. If it's a plus here, it's a plus here. If it's a minus here, it's a minus here. For the cosine function, the sign here changes. If it's a plus here, it's a minus here. If it's a minus here, it's a plus here. So sine, same, cosine changes. SSCC. Kind of works. All right. So let's go back to the first page and then we'll come, let's continue on this page. So what is interesting about these angle sum formulas, there's actually a lot of things that are interesting about them. They do come up in various places in Calc 2, typically if you're doing some trig stuff. They also actually come up they might come up when you learn about the definition or how to find the derivative of sine or cosine. These formulas do come up if you're actually proving the derivative of sine is equal to cosine or the derivative of cosine is equal to negative sine by using the limit definition, which we'll learn all about next quarter. So you might see these then, you might not, depending on the class you're taking and the teacher's teaching. They might just draw a graph or something. They might show it, but they might not. It really depends on what class and who's teaching it. But the other interesting thing we can do is we can use these formulas to find sine and cosine of new angles. Angles we haven't found sine and cosine of yet. So currently, we are capable of finding like sine and cosine without using a calculator of 30 degrees, 45 degrees, 60 degrees, 90 degrees, and other angles that have those same reference angles. But now we're going to extend it. Actually, before I do either of these, I'm going to do a different example. Let's do that one. Let's do sine of 75 degrees. And the idea, whenever you're trying to find sine or cosine of one of these new angles, you want to find two angles that you know how to deal with that add up usually or subtract to, less usually, that angle right there. So what are two angles that we know that add up to 75 degrees? Right, 30 and 45. It's usually some pretty low-hanging fruit. It's there's not a lot of choice. Well, sometimes there's more choices than others. But for this angle, it's exactly sine of 30 plus 45 degrees. And then we're just going to apply the formula. We're going to think of this angle as our A and this angle as our B. So sine of A plus B is going to be sine of A, which is sine of 30, times cosine of B, which is cosine of 45, plus, because it's the sine one, so the sine stays the same, cosine of 30 degrees times sine of 45 degrees. Let's see what we get. So sine of 30 degrees is going to be 1/2. Cosine of 45 degrees is √2/2. Cosine of 30 degrees is √3/2. And sine of 45 degrees is √2/2. Now here's something that's worth observing. In this formula, I'm going to have sine and cosine of the same angle for each angle. If I know that sine of 30 is 1/2, I know that cosine of the same angle is √3/2. So if one of them is 1/2, the other one's always a √3/2, right? Because 1/2 √3/2 is that point on the unit circle, or negative 1/2 √3/2, or negative 1/2 negative √3/2, right? The sign might change, the SIGN might change, but the values 1/2 √3/2 always go together. And then for cosine of 45 and sine of 45, we know those are the same. Cosine of 45 is √2/2, sine of 45 is √2/2. And we typically don't leave our answers like this. So I'm going to tell you all of these particular type of questions where you're using this angle sum formula, they all simplify to look almost virtually the same. They're all going to simplify to be either positive or negative √2 plus or minus √6 all over 4. It might be plus √2 plus √6 all over 4, or it might be plus √2 minus √6 all over 4, or it might be minus √2 plus √6, right? You can get any signs, but that's always going to look at this. Let's take a look. 1 times √2 is √2. 2 times 2 is 4. √3 times √2 is √6. 2 times 2 is 4. And this simplifies as the square root of 2 plus the square root of 6 all over 4. Kind of cool. I think it's kind of cool. So here's a new angle that you can find sine and cosine. Some newer calculators, some fancy calculators, will actually give you this answer if you plug in sine of 75 degrees, which is kind of cool, I think. Just like some calculators, if you do like sine of 60 degrees, will give you √3/2 instead of like 0.86, whatever. Neat. Let's do a couple more examples. This example is not going to be what I want. That's fine. Let's actually change this example. Let's change this to sine of 11 pi over 12. So you have choices here. You can either find angles that add up to 11 pi over 12 as is, which is what I'm going to do. Or if you prefer, you could change that to degrees and think of it in degrees because it might be easier. But I'm going to tell you, I like it in radians because it's actually not too terrible. I want to find two angles that add to 11 pi over 12. So I want to find two numbers that add to 11. And here's the deal. We need both of our fractions to reduce. Meaning, got some extra paper here. Meaning if I'm trying to add to 11 pi over 12, I don't want to pick 1 pi over 12 plus 10 pi over 12. Because although 10 pi over 12 does reduce to 5 pi over 6, 1 pi over 12 doesn't reduce. And I do want to pick maybe 2 pi over 12 plus 9 pi over 12. Both of those reduce. I could also pick 3 pi over 12 plus 8 pi over 12. Both of those reduce. But I can't pick 4 pi over 12 plus 11 pi over 12. Sorry, 7 pi over 12. Because though one of those doesn't reduce. So as long as you are picking two that end up reducing, you're going to get denominators that are either 3, 4, or 6, which are denominators we can handle. Yeah. So let's go with the first choice we see, 2 pi over 12 plus 9 pi over 12. So I'm going to write this as sine of 2 pi over 12 plus 9 pi over 12, which is really sine of pi over 6 plus 3 pi over 4. And those look like angles we know how to deal with. So then I'm going to write this as sine of pi over 6 times cosine of 3 pi over 4 plus cosine of pi over 6 times sine of 3 pi over 4. And that's going to be equal to, let's see, sine of pi over 6 is sine of 30 degrees, which is 1/2. So here's the thing. Sine of pi over 6 is 1/2. So I know cosine of pi over 6 is going to be √3/2. Right? I'm always making that connection that if one of them is 1/2, the other one's √3/2. But so cosine of 3 pi over 4, I know it's a pi over 4. So I know it's a √2/2. But 3 pi over 4, show me on your fingers, is in what quadrant? Not quite, too much. This many, right? 3 pi over 4 is, so, right, here's what I usually think about when I think about the quadrant. 1 whole pi is half of the way. It would have been much better if 1 whole pi was 1 full revolution. It's not. 2 pi is a full revolution. 1 pi is half a revolution. So a whole pi gets you halfway around the circle. So 3 pi over 4, or 3/4 of pi, gets you 3/4 of the way halfway around the circle. So it ends you in the second quadrant. So being in quadrant 2 means cosine of 3 pi over 4 is going to be negative √2/2 because 3 pi over 4, because cosine is negative in quadrant 2. We already said cosine of pi over 6 was going to be √3/2, and sine of 3 pi over 4, well, again, it's going to be a √2/2 because it's a pi over 4, and 3 pi over 4 is in quadrant 2, but sine is positive in quadrant 2, so it's going to be a positive √2/2. And then we simplify, we end up getting negative √2/4 plus √3 times √2 is √6/4. And I would probably write this, instead of writing it as negative √2 plus √6 all over 4, I would probably write the positive thing first and write it as positive √6 minus √2 all over 4. Although it's totally fine to write it as negative √2 plus √6 all over 4. Questions so far about this? kind of used at my room over here. That's all right. It'll be fine. So let's look at cosine of 165 as well. Oops, don't, sorry. It's kind of in the way. Oh well. So I'm going to try and think of two angles that add up to 165 degrees. Here's a nice thing to know. You can always do 45 degrees plus whatever is left over. That should almost always work, unless your angle is too small. Like if your angle is 15 degrees, that wouldn't work, but fine. So cosine of 165 degrees, we can think of as cosine of 45 degrees plus 120 degrees. So then that's going to be, I'm using the cosine formula now. Cosine of A plus B is cosine of A times cosine of B minus sine of A times sine of B. So cosine of A plus B is going to be cosine of my 45 degree angle times cosine of my 120 degree angle minus sine of 45 degrees times cosine, times sine of 120 degrees. Woo, careful there. Okay. So we know that both cosine of 45 degrees and sine of 45 degrees are going to be root 2 over 2. So this is going to be, I think I can squeeze this in here. Root 2 over 2. Oh, it's getting a little dicey there. Times, let's leave myself some room for cosine of 120. Minus sine of 45 degrees is also root 2 over 2 times whatever sine of 120 degrees is. Okay, so 120 degrees. The reference angle is 30 or 60? Not 30. It's actually 60. So if you're doing 120 degrees, draw a little picture here. 120 degrees gets me right over here. And we're always measuring our reference angle to which axis? Always the x-axis. So if we want to go all the way to the x-axis, we need, well, 1/2 a revolution is 180 degrees. So we still need 60 more degrees to get there. Or 180 minus 120 is 60. So then I can see that looking back up here, which you can't see, back up here, which you can now see, cosine of 60 degrees is 1/2. But since we're in quadrant 2, it's going to be negative 1/2. And sine of 60 degrees is root 3 over 2. And since we're in quadrant 2, sine of 120 degrees is going to be positive root 3 over 2. And the rest is just simplifying. So here I'm going to get negative root 2 over 4 minus root 6 over 4, which writing it as one fraction. Now, here's something to be a little bit careful about. I can write it as negative root 2 minus root 6 all over 4. But I want to point out that that negative sign is in the numerator there. If I wrote the negative sign out in front, it's technically having to be distributed to both terms. So if you write a negative out front, you actually have to write it like this. You write it as negative root 2 plus root 6 all over 4. Because a negative of that thing, that negative distributes to each term in the top. I don't think you should write it like this. I would write it like this, but just be aware a negative out front is a little bit different than the negative on just the first term in the numerator. Okay, so that's the angle sum formula. This is mostly what we use it for evaluating cosine and sine of some new angles, which is kind of fun. I mean, not that fun, but like it's interesting. How about that? Kind of interesting. So there are some new angles we can totally find sine and cosine of and get their exact values. So now let's go back to the first page. Back to page 1, where we can talk about some related identities, the double angle identities. Cool. So these double angle identities come from the identities we just talked about. Sine of 2 theta, well, we can think of the angle sum identity. Sine of 2 theta is really equal to sine of theta plus theta. Right? 2 theta is just 1 theta plus 1 theta. And then if we use the angle sum identity for sine of, I'll remind everybody, I know we just removed it, but right, sine of A plus B is sine of A times cosine of B plus cosine A times sine of B. So if both A and B are theta, sine of A plus B is going to equal sine of A times cosine of B plus cosine of A there. Cosine of A times sine of B. Those are the same. Sine theta times cosine theta plus cosine theta times sine theta. Those are each the same thing. So I can really think of this as sine of theta times cosine theta plus another sine of theta times cosine theta. And if you add two things together, they're the same. You really just have twice that many of the same thing. So we really have 2 times sine theta times cosine theta. I want to be extra explicit about this. Sine of 2 theta is equal to 2 sine theta times cosine theta. It is not equal to just 2 sine theta. We're not just pulling out the 2 in front of the function. We're really saying, oh, there's this identity that this thing's equal to. In the same sort of way, we can show that cosine 2 theta is equal to cosine squared theta minus sine squared theta, because we know that cosine of theta plus theta is equal to cosine of theta times cosine of theta minus sine of theta times sine of theta. But that's exactly cosine times cosine is cosine squared theta, and sine times sine is sine squared theta. So these double angle identities really just come from the angle sum identities we just talked about on the second page. And unlike the angle sum identities, we don't really use the double angle identities to evaluate sine and cosine of any new angles, right? There's not an angle that's twice an angle we already know that we don't have. Like, for example, I wouldn't use, right? Like, I'm gonna say it again because I was trying to say something I didn't say. There isn't an angle that we don't know how to take sine or cosine of that's twice an angle that we do know how to take sine or cosine of. That makes sense? Like, I wouldn't use this to find sine of 60 degrees by saying sine of 2 times 30 degrees, because I already know how to find sine 60 degrees. Right? Any angle that I would use this for, I already know how to find sine or cosine of. But what we can do is ask kind of interesting questions. And I will say, more than the formulas on the second page, these formulas really do come up when you start talking about evaluating derivatives of trig functions and intervals of trig functions. So they will come up later on, just not yet. For now, we can use them to do fun stuff like if cosine theta equals negative 5/13 and sine theta is negative, find cosine of 2 theta. Okay, so first and foremost, we know that cosine of 2 theta is equal to cosine squared theta. Oh, this one, I always forget that you could totally, there's a way you could totally get around this one if you wanted to. I should point it out. Why not? So I'll point out that for this question, you could kind of, I don't want to say cheat because it's not cheating. You could use your knowledge, say, well, I don't really need to do anything that special if I just think about the fact that sine squared theta is equal to 1 minus cosine squared theta. I should point out also, cosine squared theta minus sine squared theta is not equal to 1. Cosine squared theta plus sine squared theta is equal to 1. They kind of have some similar vibes, but they're not the same. But if cosine squared theta plus sine squared theta equals 1, then sine squared theta equals 1 minus cosine squared theta. And we could totally rewrite this as cosine squared theta minus 1 minus cosine squared theta. Or minus 1 and then minus is plus 2 cosine squared theta minus 1. Which, if I know that cosine theta equals negative 5/13, this is going to equal 2 times negative 5/13 squared minus 1. Okay, let's do some math. That's going to be 2 times 5 squared is 25, 13 squared is 169, minus 1. I'm going to need the common denominator. 2 times 25 is 50 over 169. And then minus 169 over 169. 50 minus 169 is negative 119 over 169. And that is correct. Without using any of the methods we're going to have to use to find the next thing we're going to find, which is, okay, now find sine of 2 theta. And unlike the cosine 2 theta angle, double angle identity, you don't get cosine squared and sine squared. So if I'm trying to find sine of 2 theta, which is 2 times sine of theta times cosine of theta, I totally know that cosine theta is equal to negative 5/13 because it was given to me. I have no idea what sine of theta is equal to. So I know what cosine is, and I'm trying to find sine. What I usually have to fall back on is drawing a triangle. I'm going to draw a triangle. See, that angle is theta there. And I know that cosine of theta, which is adjacent over hypotenuse, is equal to negative 5/13. Personally, when I do this, I like to ignore the negative sign, although you can totally write it if you want to. So I'm going to say my adjacent side is 5, or if you prefer, you can write a negative 5. And my hypotenuse side is 13. I'm going to use those two sides to find the unknown side, because that's what side I need to find sine of theta, because sine of theta is opposite of hypotenuse, which is going to be something over 13. My hypotenuse is still 13. So the third side here, if I call this, I don't know, z, I have that negative 5 squared plus z squared is equal to 13 squared. That's 25 plus z squared equals 169. So z squared equals 169 minus 25, which is 144, which means z is going to equal 12, the square root of 144. So then sine of theta, well, we know that sine is negative, right? They told us in the problem sine was negative. So if sine of theta is negative, this is going to have to be negative 12 over 13. So then sine of 2 theta is going to equal 2 times sine of theta, which is negative 12 over 13, times cosine of theta, which we were told was negative 5 over 13. So that's going to equal, let's see, 12 times 5 is 60, times 2 is 120. That's going to be 120 over 169. Let me ask you all two questions. Question one. If cosine is negative and sine of the same angle is also negative, so again, cosine and sine are both negative, show me on your fingers or type it in the chat, what quadrant is our angle in? If sine and cosine are both negative. I believe it's this one. Right? If we think about it, if you think about your all students take calculus, sine's positive here, cosine's positive here, they're all positive here. This quadrant, quadrant 3, is the one where they're both negative. So theta is in quadrant 3. Okay, so follow-up question. If cosine of 2 theta is negative 119 over 169, and sine of 2 theta is positive 120 over 169, or more specifically, if sine is positive and cosine is negative, what quadrant is that angle in? Yeah, exactly. So we can tell also that 2 theta must be in quadrant 2, because sine of it is positive and cosine of it is negative. In fact, I will say, whenever someone asks you what quadrant is an angle in, the usual expectation is that you find whether sine is positive or negative and cosine is positive or negative, to then use the quadrants to just determine which quadrant you're actually in. I should point out that in this particular one, if we knew that our original angle was in quadrant 3, yeah, let's just grab another piece of paper here. So I just want to show you one thing because it's kind of interesting. So if our angle is in quadrant 3, that means our angle is bigger than 180 degrees, right? Because we passed this mark here to be in quadrant 3, and smaller than what? Yes, I love that answer. I was using degrees though, so I'm going to go ahead and say 270 degrees. But you're totally right. You could also say that theta is between pi and 3 pi over 2. I just want to point out that if you then multiply all this by 2, you end up getting that 360 degrees is less than 2 theta is less than 540 degrees. 360 degrees is 1 full revolution. Add another 90 degrees, you get 450. Add another 90 degrees, you get 180 plus 360, which is 540. So the thing is, if you know that theta happens to be in some specific quadrant, doubling it means you end up having a possibility of being in 2 different quadrants. So you can never just tell by saying, well, if I double it, I end up in this other quadrant. You can't tell, because doubling an angle that's in quadrant 3, maybe your angle was less than 225 degrees, and so doubling it is less than 450. But maybe your angle is more than 225 degrees, so doubling it is more than 450. So that's kind of the way. I've seen many people over the years be like, oh, just double it, and I'm in this quadrant because twice of this angle has to be this angle. No, if we double it, we have to do a whole new exploration of, oh, what's sine? What's cosine? Are they positive or negative? Okay. Let's see. That page, that page. I feel like I wanted to do something slightly different here. I'll take one look before I get too carried away on this third page here. That's fine. Okay, so page 3, kind of more stuff we've kind of seen before. Just revisiting a little bit these hyperextended angles, which we kind of talked about a little bit already. So if you're dealing with a hyperextended angle, meaning an angle that's bigger than 1 full revolution, that's what hyperextended means. More than 1 full revolution. We still do things the same way. We're still going to find a reference angle if one exists. Not every angle has a reference angle. Like 90 degrees doesn't have a reference angle. Pi, any quadrantal angle doesn't have a reference angle. So, but for angles that do have reference angles, we're going to find the reference angle, and then we're going to figure out what quadrant the angle's in. So 59 pi over 6. Ugh. 59 pi over 6. There are a couple ways of thinking about this. Here's one way of thinking. I'm going to talk about this in 2 different ways. One way of thinking about this is it's almost 60 pi over 6. 59 pi over 6 is just slightly less than 60 pi over 6. What's 60 pi over 6 if I reduce that fraction? 10 pi. And 10 pi is 5 times 2 pi, or 5 full revolutions. So we are just 1 pi over 6 shy of 5 full revolutions, meaning if we do 5 full revolutions and then go back pi over 6, what quadrant do we end up in? Let's see. If I do 1 revolution, 2 revolutions, 3 revolutions, 4 revolutions, 5 revolutions, but then I go back pi over 6, we're in quadrant 4. So one way to do this is to say, okay, our reference angle is pi over 6, and we're in quadrant 4. Another way to get there is the following. You could just start subtracting off full revolutions. So the second way to see where you land is to take your original angle and subtract off a full revolution, which is how much? Over time. Not quite. I see what you're saying. Oh, I totally see where you're going with that. So I want to subtract off 2 pi because 2 pi is 1 full revolution. Or if you're in degrees, we subtract off 360 degrees. In fact, actually, no, let's do this. I don't want to switch gears here yet. So I'm going to subtract off 2 pi, but I need a common denominator. So I'm going to write this as 59 pi over 6 minus 12 pi over 6. So that's 2 pi. And that's going to give me 47 pi over 6. Sorry, my 7 looks terrible there. And then I keep doing it. So again, 47 pi over 6 minus 12 pi over 6 is 35 pi over 6. Do it again. If I subtract 12 pi over 6, I'm going to get 23 pi over 6. Do it again. Subtract 12 pi over 6, I get 11 pi over 6. And 11 pi over 6 is less than 1 full revolution. It's almost 1 full revolution though. Right? 11 pi over 6 is just pi over 6 short of 12 pi over 6, which is 2 pi. So we can see, okay, this is coterminal, meaning it ends at the same place with 11 pi over 6. And we know 11 pi over 6 ends up right there. The reference angle is pi over 6. Whichever way you want to slice, it's totally fine. You just have to be able to figure out how you're going to get what quadrant your angle is. I kind of know it's not, I feel like this second way we did it is a little more methodical, right? This first way we did it, we happened to notice that it was close to something that was easy to deal with. But I feel like the second way is kind of, and you don't have to do it one at a time, right? If you can see that there's more than just a 1 revolution, you can I'm going to subtract off 8 pi. Because 8 pi is 48 pi over 6. So, right, you don't have to do so many steps. In either event, our reference angle is pi over 6, quadrant is 4, and we're dealing with secant. I don't love secant. If I'm dealing with secant, I'm going to think of its reciprocal, which is what? Sine, or is it cosine? So here's what I think of it. We always have one co-function and one non-co-function. So secant isn't a co-function, right? It doesn't start with the word, it's literally just doesn't start with the letters co, C-O. Secant doesn't start with co. So it goes with which one? Sine or cosine? Cosine. You always have to have one co in each of your pairs, in each of your reciprocal pairs. So over here real quick, reciprocal pairs, sine and cosecant, cosine and secant, tangent and cotangent. So whenever you're talking about reciprocals, one of them is always a cofunction and one of them is always not a cofunction. So I'm looking for the reciprocal of secant. It's not a cofunction, so its reciprocal better be a cofunction. And its reciprocal is cosine. So I'm going to say cosine of pi over 6, because that's my reference angle, is it's either 1/2 or √3 over 2. Which one is it? I don't remember. There's some, does anyone know the hand trick for sine and cosine? It's kind of neat. I'm terrible at it personally because I always like mess it up. But the idea is basically you take your angle and so like if you're like there's a good video on it on Canvas, which you should totally watch, which is way better than what I'm about to say. But the idea is basically like you kind of label the 5 important angles: 0, pi over 6, pi over 4, pi over 3, pi over 2. And then, so like 0, so look at my hand for a second. You guys look at my hand. 0, pi over 6, pi over 4, pi over 3, pi over 2. So I'm going to pi over 6, I put that finger down. And then cosine is √3 over 2. Sine is √1 over 2, or 1/2, because √1 is 1. And it works. If you go to 45 degrees, cosine is √2 over 2. Sine is √2 over 2. If you go to pi over 3 radians, sine is √3 over 2, and cosine is √1 over 2. It even works if you go all the way to the end, right? Now here sine is √4 over 2, which is 2 over 2, which is 1. Cosine is √0 over 2, which is 0 over 2, which is 0. It's kind of a neat trick. I'm not good at it, but it works if that's something you want to remember. Back to this though, cosine of pi over 6, well, is the √3 over 2. So cosine of pi over 6 is √3 over 2. So secant of 59 pi over 6 is going to be positive since we're in quadrant 4. Because cosine's positive in quadrant 4, secant's positive in quadrant 4. And it's going to be the reciprocal of this. So secant of 59 pi over 6 is going to be positive 2 over √3, which we should rationalize by multiplying by √3 over 3 and get 2 √3 over 3. And hopefully you can do that a little bit faster than I was able to explain it to you, because it's a lot of explanation, but with purpose. Okay, secant again, who's writing these problems? Secant of 99 pi. So we recognize that 99 pi is a multiple of pi, which means we're going to end up on one of the axes, top, bottom, left, or right. So here's what I'm always thinking about. If it's a multiple of pi, it's either going to be over here, like 0 or 2 pi or 4 pi or 6 pi. I'm just going around, or over here, pi or 3 pi or 5 pi or etc. So which side are we going to end up on the right or on the left if it's 99 pi? Because it's an odd multiple of pi. So all the odd multiples of pi go here. All the even multiples of pi go here. The top and bottom are a little bit harder. Not that we need to do them for this problem, but just so you know, the top is going to be like pi over 2, 5 pi over 2, 9 pi over 2, etc. It's all the odd multiples of pi that are, I don't know, multiples of 4 plus 1, 0 plus 1, 4 plus 1, 8 plus 1, over 2. And then down here, it's the other ones, the 3 pi over 2, the 7 pi over 2, etc. These are all the odd multiples of pi over 2, where the odd number is a multiple of 4 plus 3. Not the easiest way to describe it, but that's kind of the easiest way to describe it, unfortunately. Anyway, we're looking at this number here, 99 pi. We've gone around. How many times have we gone around? If we've gone to 99 pi. Have we gone around 99 times? 2 pi is the whole revolution. So we've actually gone around 99 divided by 2, which is 100 divided by 2 is 50. So 99 divided by 2 is 49 and a half. So we've gone around 1, 2, 3, 49 times and a half. Gets back over here. You don't need to do that or think about that, but it's just good to know what's happening. So again, with secant, I'm going to think of cosine. Cosine of 99 pi. Well, at this point, our coordinate is -1, 0. So cosine of 99 pi, is it -1 or is it 0? Think alphabetically here. Yeah, well, -1. Yeah. Cosine of 99 pi is -1. So secant of 99 pi is -1. Sorry, apologies. Is the reciprocal 1 divided by -1, which is also equal to -1. And since we're already over there, let's talk about sine and cosecant. Sine of 99 pi would be 0, and cosecant of 99 pi, which is its reciprocal, the reciprocal of 0 does not exist. Let's see. Yeah, let's do one more example. Let's go back to the angle sum stuff. So the question I want to ask is, what is cosine of 53 pi over 12? So that is definitely a hyperextended angle. You could, although I don't really recommend it, you could find angles that add up to this because, oh, actually, I should back up. How do I know I'm going to have to use the angle sum formula? It's a really good question. How do you know when to use the angle sum formula? Well, here's a clue. You need to use the angle sum formula if you see the following. If your angle in radians is something over 12. So the angle in radians is something times pi over 12. It can be any integer number. So it could be whatever you want going there. Or in degrees, your angle in degrees is something like 75 degrees or 165 degrees or 195 degrees or something that's 15 degrees away from one of your axes, which is the same as pi over 12 radians. So if you're 15 degrees off from any axis, x or y axis, you're going to use this angle sum formula. It's easier. That's why I kind of like doing it in radians, because it's kind of easier to tell range. Like 53 pi over 12 in radians, or sorry, in degrees, is kind of extremely terrible. Like it's not that terrible, but it's not great. It's, I don't know what it is. Let's find out. 53 pi over 12 times 180 over pi. Pi's cancel. 180 divided by 12 is 15. That's going to be 53 times 15 degrees. Yeah, 53 times 10 is 530. 53 times 5 is half of that, which is 265. That's going to be 795 degrees. And I have no way of knowing where that actually falls on the circle, right? Maybe that's an angle I'm good at. Maybe it's not an angle. So I feel like degrees here is not super duper helpful unless you start finding an angle that's coterminal with. So I'm going to take 53 pi over 12. And I'm going to start subtracting off some 2 pi's. In fact, let's be more bold. I can see that there's a whole 4 pi worth of subtraction I can do there. Because 53 pi over 12, 53 divided by 12 is bigger than 4. Like 4 point something. So I'm going to subtract off 4 pi. And say that's 53 pi over 12 minus 48 pi over 12, which leaves me with 5 pi over 12. I want to stress 53 pi over 12 and 5 pi over 12 are not the same angle. They are coterminal, meaning cosine of 53 pi over 12 is equal to cosine of 5 pi over 12. But these angles themselves are not the same. They're just ending up at the same place. And it is almost, so then we would do this as cosine of, say, like 2 pi over 12 plus 3 pi over 12. And then we would reduce and say it's cosine of pi over 6 plus pi over 4. And then we would say it's cosine of pi over 6 times cosine of pi over 4 minus sine of pi over 6 times sine of pi over 4. And then we would get cosine of pi over 6 to be root 3 over 2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 6 is 1/2. Sine of pi over 4 is root 2 over 2. And then we would get root 6 over 4 minus root 2 over 4, which is root 6 minus root 2. Again, all these answers end up looking the same at the end. It just depends on what the signs are. It can be positive root 6 plus root 2 over 4, or positive root 6 minus root 2 over 4, or root 2 minus root 6, right? You've got 4 options, really. Positive root 6, positive root 2, positive root 6, negative root 2, negative root 6, positive root 2, and negative root 6, negative root 2. Those are kind of the only 4 things that can happen for these, which is kind of cool. So whenever you're using an angle sum formula, whether it's on your homework or on a test, you should be aware that your angle should always look like, your answer should always look like something with a root 6, something with a root 2, all divided by 4. Kind of nice to know what your answer should look like. All right, that's all I've got. Hope you all have a lovely break. See you all on Monday for the last week of class. And then finals are after that. And I will try to get your homework, not your homework, your exam graded. I've already graded like a third of it, so I'm pretty close to not. I'm getting there. It's supposed to be more. So the final will be, I would say, will be more heavily focused on essentially the trig, because that's really all that's since midterm 2. So the final will be, I don't want to say primarily trig, but it'll be substantially trig, but it is supposed to be cumulative, so there probably will be some stuff from the past as well. Yeah. All right. Travel safely. Easy.